in some sense, interstellar clouds is where the whole origin of life started, not necessarily because life itself started out there, but because stars and planets began their lives, originally as interstellar clouds. This is one of the most famous ones. It's the Orion Nebula, which is down there in the part of the Sword of Orion. So it's very easy to see just with a pair of binoculars or even with your naked eye. So this is one of the nearest star-forming regions. Here's another even more famous nebula here. This is one of the most famous Hubble Space Telescope pictures that was ever taken. It's part of the Eagle Nebula. And so you see these giant, it's sometimes called the pillars of creation. You see these giant arms of the nebula that reach out into space and that are backlit by some very bright young blue stars. So it's a very spectacular star-forming region. And then finally, I'll show you one more. This is another favorite. This is the Horsehead Nebula, which is named for obvious reasons. As the slide shows, these interstellar clouds not only are the birthplaces of stars, but they also contain a lot of organic compounds. And so that makes them more directly relevant to the origin of life. That's a lot of what you're going to hear about this morning from our first and fourth speakers are both going to talk about the interstellar cloud chemistry. And I have already, as I said, I'm not really, my own background is not in this subject, but I learned things. I went on one of the excursions this weekend to the Canal de Midi, and Sun Kwok, who's our third speaker this morning, we bent my ear, and he will talk about the source of the organic compounds in these interstellar clouds. The source could either be from cloud chemistry itself, or some of these organics may be made in the expanding envelopes of dying stars in what are called planetary nebula. And then they reseed these clouds. So stars themselves may play a large role in forming the organic compounds from which life ultimately arises. Now, of course, to get to life, you have to do things with the clouds. They collapse. They're spinning, and so as the cloud collapses, it spins out to form a disk. And we will hear maybe a little bit about that, but there's probably more in the poster session. These disks used to be hypothesized, but they're now observable because we have sufficient resolution with telescopes. So this is one of the first, I think it was the first disk to be imaged. It's called Beta Pic. It's a disk around the star Beta Pictoris. You can see a scale bar here that shows the size of Pluto's orbit or Neptune's orbit. So this disk is larger than the size of the solar system. It's a very clear evidence. You're looking at it edge-on, so you can really see that it's disk-shaped. In fact, if you look carefully, it's a little warped, and that's possibly because it has planets growing in it that perturb the disk itself. Now, to get to planets and stars, the star forms from the central part of the condensation. The planets form from the disk. And of course, what happens is that solid particles begin to condense out of the disk. They fall down to the midplane of the disk, and there's some kind of distribution. But there they begin to collect into planetesimals. And the planetesimals grow larger and larger and eventually turn into planets. Now, in the latter stages of accretion, this process of planet formation is termed accretion. In the latter stages, the planetesimals grow relatively large. They're nearly to their final stages, and they have enough gravity then to influence each other, and all sorts of interesting things can happen during this latter stage of planet formation. Some of the most interesting things that the planetary scientists have been talking about for the last 5 or 10 years are part of what is called the Nice model, Our second speaker this morning, Alessandro Morbidelli, is from Nice, and so the Nice model is really, partly his group and people that work with Morbidelli and his group. This shows some of their early results, and this was a paper that was published now 6 years ago in Nature, showing in the upper panel the outer 4 planets of our solar system. And if you can't read it, this is time, actually going the first billion years of solar system history, starting at the left. Uranus, Neptune, Saturn, and Jupiter. These are their semi-major axes here, their mean orbital distances. And what you see is that these planets are going around. Actually, they're migrating slightly. Saturn, you may know, is slightly, its orbital period today is just over twice that of Jupiter. But in the Nice model, the Saturn and Jupiter start closer together, and the orbital period of Saturn is less than twice that of Jupiter. So as Saturn moves out and Jupiter moves in slightly, they go through this 2-to-1 mean motion resonance where Saturn's orbital period is exactly twice that of Jupiter, and at that point the gravitational interactions become very strong, and they excite each other's eccentricities, and that in turn perturbs the other planets. And notice that Uranus and Neptune, they're in the wrong order right here. Uranus is inside Neptune today, inside Neptune's orbit. But in the Nice, at least in this version of the Nice model, Uranus and Neptune flip positions and they get tossed farther out into the solar system. And when that happens, they perturb all the planetesimals that are out there, these icy bodies that we call comets. And so the bottom panel shows the flux. Some of these bodies come back through the inner solar system and give rise to what is termed the heavy bombardment that we see evidence for on the Moon and Mars, and which almost certainly happened on Earth as well. So in this particular model, you get a big pulse of bombardment around 3.8 or 3.9 billion years ago, and that may or may not have been an important factor in influencing the origin of life. It's possible that that could have extincted life that was present at the surface, although we know that life can colonize the subsurface, so there life may have originated before then and then colonized the subsurface and survived this bombardment. As part of the accretion, you can also, in some models, keep track of the volatiles. These are some calculations that were done several years ago by Sean Raymond and colleagues. And so what Sean shows in this picture, these are time slices of an accretion model going from 0 to 200 million years into accretion. This is semi-major axis on the horizontal axis and the planetesimals' eccentricities on the vertical axis. These planetesimals are color-coded. Sean starts them out with different water contents. And so we think that the water starts from farther out in the solar system in the asteroid belt region or beyond, out here where these blue-colored planetesimals are. And then as he starts his simulations, these planetesimals move around. As time goes by, they start to mix with each other. And by the time you get to the end of accretion here, you've got 3 planets in the terrestrial planet region, all 3 of which have some of this water that came from farther out in the solar system. And this leads to a question which will lead into the second half of the session: is water really necessary for life? That's I think one of the fundamental questions of astrobiology, which we talk about a lot, but we don't really know the answer to at this point. Let me just say a couple words about life. In the second part of this session, after the coffee break, we'll hear more about life. One of our speakers is Jerry Joyce. Here's a definition of life that Jerry is credited with. Life is a self-sustained chemical system capable of undergoing Darwinian evolution. Well, that's actually a very nice definition, one that I think NASA likes. It's a definition that I like. But that's most suitable for looking at life in situ. So if you're in a laboratory, Jerry and others are essentially trying to create life in a laboratory, and maybe you could create some system that followed this definition. If you're looking for life out there in the universe, though, then you probably need another definition because this is not something that's easily testable by remote observations. So what observables are there that are required for life? We don't really know the answer to that, but I'll mention two of them. The first one, and I would argue that this is actually an absolute requirement, is that I think that life requires some kind of rocky planet, or a planet with a solid surface. And so this rules out gas giant planets like Saturn or Jupiter. Why is that? Well, it's because on a gas giant planet, there is no stable pressure temperature regime in which to originate life or for an organism to survive. So some type of incipient life form would be threatened with being wafted up to the very cold fringes of the atmosphere, or alternatively carried down to depth where it would be burned up. And so I think that means that the search for life on other planets should be concentrated on planets that are at least Earth-like enough to have a solid or liquid surface. And then, of course, the other requirement for life on Earth as we know it is liquid water. All life on Earth it's all carbon-based, of course, and it requires liquid water during at least part of its life cycle. So back to this question, is water a universal requirement for life? As I said, we don't know the answer to that. There are posters. In particular, there's one in our session by Pohoriel and Pratt that addresses this question directly from a chemical standpoint. And so I think we'll leave that for questions. I'm not going to take questions myself because I want to get on to the talks. But let's now start then with we'll have our first talk on interstellar cloud chemistry.